In this video, we are going to talk about special cases of when we're taking integrals. So in the last video, we talked about contour integrals, and that's the most general, always works approach to taking complex integrals with complex variables. However, this is a special case. There are two different cases. One is when it concerns antiderivatives, and the second special case is the Cauchy-Goursat theorem. So the first theorem relating antiderivatives is suppose we have a function f of z and it's continuous on a domain. Wherever it's continuous on the domain, if any of the following statements is true, then so are the others. 1. F of z has an antiderivative, and that antiderivative is capital F of z throughout the domain D. 2. The integrals of f of z along the contours lie entirely in D, and extending from any fixed point to z1 to any fixed point z2 all have the same value. So all the contour integrals then are simply equal to the antiderivative, capital F of z, evaluated at z2 minus z1. 3. The integrals of f of z around the closed contour lying entirely in D all have zero values. So again, if it's closed, then z1 equals z2, and our subtraction here will give us 0. So the idea is once we have a function f and it's continuous on a domain D, if the antiderivative exists throughout the entire domain D, then these two parts of the theorem apply. And actually, if any one of these is true, A, B, or C, it implies that the other two are true. And our first example of this theorem is if we have a curve C, which is the positively oriented curve, Z equals 2e to the I theta, where theta goes between negative pi and pi. So this is a circle of radius 2 centered on the origin. It goes from negative pi to pi. And actually this is, because it includes the endpoints pi and pi, it's a complete enclosed circle. So the fact that I have a gap here, just ignore that. So we know that 1 over z squared is continuous everywhere except at z equals 0. So I have this blue dot. So that we're going to omit from our domain. So our domain is everywhere except z equals 0. Then our antiderivative, which is equal to minus 1 over z, exists throughout our domain D. It exists everywhere except at the z equals 0. So we're good to use this theorem now. And then if C, since C is a closed curve, it's a complete circle, that means part C applies. So the integral around the closed curve of 1 over z squared dz will be equal to 0. So you know how I said at the beginning of this video that when we learned how to integrate around a contour for complex valued functions with complex variables, you might ask, well, why do we need to learn these special cases? Well, as you can see, this special case really simplifies the calculation. You can certainly parameterize the contour as we did in the previous video, and then you can do f of composed of your contour, and you can do the derivative of your contour, and then you can plug those both into your formula for the integral and integrate. But gosh, this is just so much easier. So again, the idea I wanted to tell you is those contour integrals will always work, but these special cases, when they apply, really do simplify everything. The second example, and actually a couple of these examples, bring in the idea of multi-valued functions in their branch cuts. So if we have the same curve, z equals 2e to the I theta, this circle, radius 2, centered around 0. If our function now is equal to 1 over z, then the antiderivative is equal to log over z, which we have learned is a periodic function and therefore a multi-valued function. The other very common multi-valued function you will see is the square root of z. Because you have the positive and negative square roots, it's also multi-valued. But anyway, so log of z is multi-valued. And for doing these derivatives, for doing integrals, you need to choose a branch. And in general, our branch cut for log is going to start at 0 and then radiate out. So I have this example worked out in detail later on in our video, so we'll look to see what to do with this sort of thing with branch cuts. Our second theorem that simplifies these contour integrals is the Cauchy-Goursat theorem. So if a function f is analytic at all points interior to and on a simple closed contour C, then the integral around a closed curve is equal to 0. And this is what it looks like written as a formula. So this is very similar in result to part C, and that it's about closed contours and that the integral around the closed contour is equal to 0. The difference of this is the conditions that need to be met for the Cauchy-Goursat is a little bit different than the conditions that need to be met from this theorem. So if you can't apply this theorem, it's worth looking at the Cauchy-Goursat. And also, I just have a note of what it means to be analytic, and we talk about that more also in this video. So that's the introduction, and we can continue with the main content now. Our first theorem for this video is suppose that a function f of z is continuous on a domain D. If any one of the following statements is true, then so are the others. 1. F of z has antiderivative, capital F of z throughout D. 2. The integrals of f of z along the contours lying entirely in D and extending from any fixed point z1 to any fixed point z2 all have the same value. That is, the integral from z1 to z2 of f of z dz is equal to capital F of z, the antiderivative, evaluated at z1, z2, or f of z2 minus f of z1. And then this here is an extension of the fundamental theorem of calculus that you're familiar with from first year calculus. And then the last equivalent statement is the integrals of f of z around any closed contours lying entirely in D all have 0 value. I am going to use this example of f of z equals z squared to look at this first condition and then the second statement here. Once we've looked at that, we'll talk a little bit more about this third statement. So let's consider f of z equals z squared. So this function is continuous, and we can find an antiderivative, capital F of z equals 1/3 z cubed. And so f prime of capital F of z is equal to little f of z. And this is true throughout the plane. So here we have little f of z has an antiderivative, capital F of z. Throughout here, the domain D is the plane. Hence, by this theorem, if we take the integral from z1 to z2 along any contour lying entirely in D, so as long as our contour is entirely in the plane, and we're going from 0 to 1 plus I, we didn't talk about what the path should be. It could be a straight line, it could be half an arc, it could be something crazy, okay? But basically, the integral along the contours lying in D and extending from any point z1 to z2 all have the same value, and it's given by this formula here. So in our example, we're going to go from 0 to 1 plus I of f of z, which is z squared, which we said was continuous and has this antiderivative throughout the plane, is equal to, then we take capital F of z, the antiderivative, z cubed over 3, evaluated at 0 and 1 plus I. So then I plug in 1 plus I cubed divided by 3, and this is my final answer. And that's essentially part A and part B. So I use the fact that my function satisfied part A, and that will imply that part B, this formula here, which is an extension of the fundamental theorem of calculus, is true. This last statement, saying the integral around a closed contour lying entirely in D all have value 0. So in other words, if instead of going from 0 to 1, if instead we had some path going from 1 plus I, some crazy path, maybe even just a circle that comes back to 1 plus I, so something, again, that starts at the same place it finishes, that's the definition of a closed contour. When we do our integral using part B, then we would have z1 to z1 f of z dz, which is capital F of z1 minus capital F of z1, which will equal 0. So that's what this last statement says. So again, these three statements are all equivalent. If we know A is true, then we know B is true. Or if we know A is true, then we know C is true. And vice versa. If we know B is true, then C is true. If we know C is true, then A is true. It kind of keeps going around in a circle. But once one is true, the other two are true. I want to remind you that you can't apply this to everything. In just our last video, I believe it was our last video, we integrated this function, f of z equals z of y minus x minus I, 3x squared, first over c2, and c2 was this path from 0 to 1 plus I. And then we integrated over c1, and c1 was this path from 0 to I, and then from I to 1 plus I. And for the two integrals, we got different solutions. So it was not the case that the value of the integral just depended on the endpoints 0 and 1 plus I. It depended on the path. And this theorem here does not apply because f of z here is not continuous because of this on this integral, this contour. Because this contour is not continuous at these, it's piecewise continuous, but is not continuous in the domain. And since it's only piecewise continuous, the antiderivative is not defined at these kind of where the lines join. Our next example, we have C is a positively oriented circle, z equals 2 e to the I theta, where theta goes between negative pi and pi. So here's our circle, and it actually is closed over here because it includes the endpoints. Our function then, f of z is equal to 1 over z squared. So this is continuous everywhere except at z equals 0. So our domain is going to be everything except this one point. Now, in this domain, we have f of z, our antiderivative, is equal to negative 1 over z. And by this theorem, because it's a closed contour, the integral around c is going to equal to 0. The integral around c of 1 over z squared will equal to 0. But now let's continue and say, let's consider the same oriented curve, the circle of radius 2, going from negative pi to pi, and now we have f of z is equal to 1 over z. So here we have capital F of z is equal to log of z. So the thing about log of z is it's a multi-valued function, and f of z is not defined along its branch cut. Remember, for the principal branch cut, theta needs to be between negative pi and pi, but not including pi. So let me just write that. For the principal branch cut, we have theta between pi and pi. So theta is, in this case, our antiderivative is not defined at this point. So our curve does not lie in any domain throughout which the antiderivative is defined, and we cannot make use of the antiderivative. However, we can break this circle into two curves. We can integrate from C1, this half, the right half of the circle, and then integrate C2 using a different branch cut. So our first curve, C1, the right-hand side, we can use the principal branch over here because it doesn't intersect this branch cut at the where we're on the x-axis, the negative x-axis. In other words, where theta is exactly equal to negative pi. So using the principal branch, capital F of z, the antiderivative, is equal to log of z, which is equal to natural log of r plus I theta, where r is greater than 0 and theta is between negative pi and pi, not including, there's no equality here, negative pi. And that will serve as our antiderivative of 1 over z. Again, the principal branch is going to be our antiderivative. So now when I take the integral of 1 over c, 1 over z dz, now I'm going from negative 2i to positive 2i. And my antiderivative is going to be log of z evaluated at negative 2i and positive 2i. So log of 2i minus log of negative 2i. On our principal branch, 2i, it's over here, that's going to be equal to, well, I, just the direction, is equal to e to the I pi over 2. And that's good. It's within our principal branch. So 2i is just 2 times e to the I pi over 2. Our negative I down here is just going to be negative I pi over 2, right? So we have, so here this is, and negative 2i is just negative 2 times e to the I pi over 2. So here, natural log of 2i is natural log of 2 plus I pi over 2. This is just using the definition of log. And then we subtract using the definition of log. This becomes natural log of 2 minus I pi over 2. And again, this pi over 2, this minus pi over 2, those are on the principal branch. So what we get is pi over 2. For C2, we're going to use the branch log of z is equal natural log of r plus I theta, where r is greater than 0, and theta now is going to be between 0 and 2 pi, not including 0 or 2 pi. So our branch cut is over here, so it does not intersect our C2. So when I integrate of C2 1 over z dz, I'm going from z1. So my first value is here, 2i, and then z2, my second value, we get to is minus 2i. This is like, I don't know why, this always throws me off, but remember, you're going from z1 to z2. So z1 in this case is the higher number, that's the one on bottom, and then the lower number is where you end up. And now, that's equal to log of minus 2i minus log of 2i. And you notice also, because I'm not on the principal branch, my log I have as a lowercase l. The principal branch, it's notation, tradition, it's, the form is you write it with a capital L when you're on the principal branch. The principal branch being theta's between negative pi and pi. Now when I convert my minus 2i, when I convert essentially minus I, because the 2 is just going to be multiple in front, when I convert minus I, I'm going to use e to minus 3 pi over 2, right? So starting here, we can go to 3 pi over 2, and that's minus I. You notice here that the angle minus pi over 2, if we went backwards, we would be, we can't have this minus pi over 2 because that's not in my range for this branch that I'm using. Okay, I'm only using theta between 0 and 2 pi. Then similarly, when I look at 2i, that's over here, that on the principal branch is just pi over 2. My I is just pi over 2. So what I have for log of minus 2i, using the definition of log, is natural log of 2 plus I 3 pi over 2. And then here I have minus natural log of 2, and now I have a plus I pi over 2. Adding these together, I get pi, I pi, or pi I. And my final answer I put over here because I was running out of room. So I add these two together to get my entire circle. So the integral over the circle of 1 over z dz is equal to 2 pi I. This example not only illustrates this theorem, but it tells us what to do when we have a multi-valued function where we have to choose a branch. And again, the reason why we had to choose a branch in this case is our capital F of z, our antiderivative, was a multi-valued function. When we chose a branch, whatever branch we would have, right, for this multi-valued function, was going to intersect the circle at some point. This branch, then the circle would be intersected here. If we chose this branch, the circle would be intersected right on the branch. And so we didn't have a domain. F of z would be continuous on the domain, but then it would not have a antiderivative throughout the domain. So what we had to do was change our contour because we wanted the contour to lie entirely in a domain where f of z would exist. So we changed our contour and we broke it up into two halves, and each half had a different branch cut, so that then when we went around the contour, we wouldn't intersect the branch cut, and our antiderivative would be defined. Our next example is the contour integral z to the 1/2. Again, another multi-valued function, dz, where c is any contour from z equals -3 to +3. And you can see from my drawing in this red line, which is my branch cut, I'm already thinking about the fact that z to the 1/2 is a multi-valued function. Here I have my f of z equals z to the 1/2. I put it in exponential form, re to the I theta raised to the 1/2, which is the square root of re to the I theta over 2. R is equal to 0, and I chose my branch now to go from 0 to 2 pi, not including the 0, 2 pi line. So my branch cut here is in red. So again, f of z is a multi-valued function. The branch 0, or theta goes from 0 to 2 pi, is not defined at theta equals 0, or theta equals 2 pi. In particular, the branch is undefined at z equals 3, which is e to the I, or 3 times e to the I 2 pi, or 3 times e to the I 0, either one. Here I've chosen another branch, so my new function f1 of z is equal to the square root of r e to the I theta over 2, r is greater than 0. Now my branch now is going to go from negative pi over 2 to 3 pi over 2, not including 3 pi over 2, so not including this red line. But now you can see my C1 path isn't on the branch cut, and my 3 and my -3 are not on the branch cut. So this would be a bad branch cut for this green path, but it's just fine for C1. So I have, again, my f of x is equal to, I need the antiderivative of my f1 of z, and I just kind of noted if these were real numbers, the antiderivative of x to the 1/2 is 2/3 x to the 3/2. So here, my antiderivative of f1 of z should be 2/3 r square root of r e to the I 3 theta over 2. Also, this step here was totally unnecessary, but I just used it to help me figure out the antiderivative. For whatever reason, when I see it in this form, it looks strange to me. So I just wanted to see what it would look like if it were real, and that helped me figure out the antiderivative for my complex function. Now I'm ready to set up my integral along C1 is equal to the integral from e to the I theta, e to the I 0. I'll make a comment on this in a minute. And then I have my antiderivative. I'm sorry. I was just putting in my f of z, square root of r, e to the I theta over 2. And that's equal to my antiderivative, 2/3 r square root of r, e to the I 3 theta over 2, evaluated at e to the I 0 and e to the I pi. And now, because everything is in this exponential form, because we are trying to make sure we're on the correct branch cut, the other thing I had to do was convert my -3 and 3 to exponential form. So I need 3 expressed as an exponential form with theta between negative pi over 2 and 3 pi over 2. So 3 theta equals 0 is just fine. It's within the range. So 3 is going to be e to the I theta. And then my -3, normally I would define that with a theta going from here to here as pi, and that's also within this branch cut. So here's my e to the I theta, which is -3. And again, our curve goes from -3 to 3, which is why e to the I theta is at the bottom, and then e to the I 0 is at the top. From there, you can see I've taken the derivative, done the algebra, and my final answer is 2 square root of 3, 1 plus I. We have one more theorem to talk about, which is the Cauchy-Gorsat Theorem. So if a function f is analytic at all points interior to and on a simple closed contour C, and if f prime is continuous there, then the integral around the closed curve is equal to 0. The Cauchy-Goursat is very similar in part C of this theorem, and that they both talk about closed contours having zero values. The difference for the Cauchy-Goursat is the conditions you need to satisfy are slightly different. So it's just another set of conditions that you can satisfy to show that integral around a closed curve is equal to 0. So I have the Cauchy-Goursat theorem here again. If a function f is analytic at all points interior to and on a simple closed contour C, then the integral around the closed curve is equal to 0. And so I have the formula here. And also, just for your reference, because this is from a different chapter, which I may or may not have made a video of by now, but a function f of a complex variable z is analytic at a point z naught if it has a derivative at each point in some neighborhood of z naught. And just to illustrate what an idea of a neighborhood is, you're actually familiar with it. In the real numbers, a neighborhood is just an open interval around a number. So the idea is that a point is analytic if in some small, and a neighborhood could be very small, some small open interval, your function behaves well. And the idea of a neighborhood in the complex plane, now instead of x being just on one axis, your z naught is in a plane, so it's a two-dimensional object. So your neighborhood can't just be this open interval on one axis. It's going to be this dotted circle, and it's dotted because it doesn't include the boundary, but it's everything inside, and actually I should say disk. It's not a circle because the circle is exactly the boundary. The disk is everything inside the circle. So in this, and this can be very small, the neighborhood could be very small, but in some little disk, an open disk around your z naught, you want things to behave well. In other words, it has a derivative at each point in some neighborhood. Here is an example. If C is a closed curve and we want to integrate e to the z cubed dz, the first thing we note, e to the z cubed is analytic because it has a derivative, 3z squared e to the z cubed everywhere. And so if C now is a simple closed contour, then it satisfies our Cauchy-Goursats. F is analytic at all points interior and to, and it's analytic everywhere. So it's analytic on the closed curve, interior and on the closed curve. We have an f prime that's continuous there. Then we can say the integral around the closed curve is equal to 0. To review the material we have covered in this video, first we talked about the fact that there are certain functions whose integral from z1 to z2 have values that are independent of the path. In particular, looking at antiderivatives, the theorems below are useful for determining when an integration is dependent or independent of a path. Moreover, when an integral around a closed path has 0. So this first theorem, suppose that we have a function f of z, it's continuous on a domain. Then if any one of the following is true, then so are the others. First, if f of z has an antiderivative, capital F of z throughout D, then you can conclude the integrals of f of z along contours lying entirely in the domain and extending from any point from z1 to z2 have the same value. And the integral from z1 to z2 of f of z is equal to this antiderivative evaluated at z1 and z2. And again, the idea is that once you have f of z is continuous on a domain, that there's an antiderivative that exists throughout that domain. The next statement that is equivalent to both of these, the integrals of f of z around closed contours lying entirely in D all have value of 0. So in other words, if f of z has an antiderivative throughout the domain, then if you have a closed contour, its value is going to be equal to 0. And you can see that when you plug into this formula, if z1 equals z2 because it's a closed contour, then your value is going to be 0. And one other note, when we say that if any one of the following statements is true, so are the other two, that means any one of these statements implies the other two statements. And we had some examples, and one thing to note about a couple of our examples, they also included branch cuts and multi-valued functions. So it's sort of a review of that topic too. If you haven't seen that video, you might want to look at that before doing all the examples. Anyway, if C is a positive oriented curve, Z equals 2e to the I theta, where theta goes between negative pi and pi, then we can see that 1 over z squared is continuous everywhere except at the point z equals 0. Then f of z, so 1 over z squared has an antiderivative, which is equal to negative 1 over z. And this is also defined everywhere in the domain, because the domain is everything except 0. So 1 over z is good, which means then, because this is a closed curve, and for this example, we would close it, it's a complete circle, that means we have part A was true here, so that implies part C, that the integral around the entire circle will be equal to 0. We then did another example where we had the same curve, but we had f of z equals 1 over z, which is when we take the antiderivative, we get log of z, which is a multi-valued function, and so it's not defined along the principal branch cut. So at this point, we were talking about branch cuts and then defining a path. So here is the summary of that example, and we covered it in more detail in our video. The next theorem we talked about, because this was the Cauchy-Goursats, which said if we have a function f that is analytic at all points interior to and on a simple closed contour C, then the integral around the closed curve is equal to 0. And this is just what it is written out as a formula. So it's similar to part C of this theorem, in that it tells us when an integral around a closed contour is 0, but it gives us the conditions that need to be met to apply this theorem is a little bit different than this other theorem. So it's like an alternate way of coming to this conclusion. And we had this example that e to the z cubed is analytic everywhere. So if C is a closed contour, we can apply the theorem, and the integral around the closed contour would be equal to 0. I didn't have any extra problems to give you because these two sections did not have any problems. So maybe later I will take a look and see if I can find some, but for now, that's it for this video. Thank you for watching.